This is my second lecture on alkyl halides. In my previous lecture, I had discussed nomenclature and classification of alkyl halides. Today we shall be discussing preparation of alkyl halides. And we know alkyl halides can be prepared by various methods, that is, by reaction of alcohols with halogen acids or reaction of alcohols with phosphorus and sulfur halides. The second method of preparation is from alkenes, that is by addition of halogen acids to alkenes. Third method of importance is from Hunsdiker reaction, which is a step-down reaction. And we have many more reactions, many more methods of preparation of alkyl halides. But today we shall be discussing in detail preparation of alkyl halides from alcohols. As you can see on your screens that alcohols on reaction with acids, halogen acids like HCl, HF, HBr, or with halides like thionyl chloride or phosphorus chlorides like phosphorus trichloride or phosphorus pentachloride results in the formation of alkyl halides. So these are the common methods by which we can convert alcohols into alkyl halides. That is, alcohols on reaction with HBr will give us bromoalkanes, whereas with HI we will get iodoalkanes, with HCl we will get chloroalkanes, but these methods are not very good because in this we are using halogen acids, that is, we are doing the reaction in acidic medium. So the preferred methods for preparation of alkyl halides are when we treat alcohols with halides like PBr3 in presence of pyridine, phosphorus pentachloride in presence of pyridine, or alcohol with thionyl chloride in presence of pyridine when we get good yields. Now we know that the reaction of alcohol with an halide anion is a nucleophilic substitution reaction. That is, when we carry out the reaction of alcohol, say with HBr, so it is an example of nucleophilic substitution reaction in which bromide anion will act as a nucleophile. So we say a halogen, usually a chlorine or bromine, replaces a hydroxyl group attached to carbon, resulting in formation of alkyl halide. As you can see on your screens, I have shown you a reaction where an alcohol is reacting with an halogen acid, resulting in formation of alkyl halide and water. This is the general representation of a reaction. This reaction as such seems to be very simple, but it is not so, because OH is a bad leaving group. It is not a good leaving group because OH minus is a strong base, and we are replacing this with an anion which is a halide anion. So this reaction is not possible. So what we have to do now is that we have to convert this OH into a good leaving group or into a better leaving group. So how can we do that? We convert OH into H2O, and H2O positive when it is eliminated as water molecule. So now you should keep in your minds that alcohol cannot undergo nucleophilic substitution reactions in neutral and basic conditions because it has a strongly basing leaving group which is OH. So it is not a good leaving group and it cannot be replaced by a nucleophile such as bromide. So this reaction is not possible. So what we have to do now is we have to convert this OH into a better leaving group. So how can we do that? We will carry out the reaction in presence of an acid. That can be we can carry out the reaction say with HBr, or if we are carrying out the reaction with HCl, then we will carry out in presence of Lewis acid. That is, we can carry out the reaction with a mineral acid or reaction of acid in presence of, say, in a presence of Lewis acid. So what is the way, how will we convert this OH into a better leaving group? For this we carry out the protonation. So when we carry out the protonation of a OH, it is converted into water, which is a weak base, and since it is a weak base, it is a good leaving group. So it is so much weak that it can be replaced by a nucleophile. But this substitution reaction is slow and it requires heat, and it will take a comparatively longer time to complete. So here what I have shown on the screen, that alcohol is reacting with HBr. In the first step, what is happening? Protonation of methanol is taking place, resulting in the formation of oxonium ion, and then a bromide will make a bond with this carbon through SN2 mechanism, which we will be discussing later on in great details, and water will be eliminated. That is, OH will be replaced by H2O will be replaced, which is a good leaving group, by a bromide anion. So since halides are strong, are anions of strong acids, so they are weak bases. So when we take a solution of HBr, HCl or HI, it will contain nucleophilic anions such as bromide, chloride or iodide. So these are the acids which are commonly used to convert alcohols to their corresponding alkyl halides. Now the question arises, what is the order of reactivity of these hydrogen halides? So it will parallel their acidity. That is, HI is the strongest acid, followed by HBr, and then that is HCl. So the decreasing order of nucleophilicity of the bases will be, iodide will be the strongest nucleophile, followed by bromide, followed by Cl minus. See, now here I am using two terms, nucleophilicity and bases. So what do we mean? That a bromide anion can act as a nucleophile when it makes a bond with carbon atom, and it will act as a base when it makes a bond with proton. So a same anion can act as a nucleophile as well as a base. So for a nucleophile to be a good leaving group, it has to be a weak base. And now if we talk of the reactivity of alcohols, what you have to remember, that among the various classes of alcohols that we are talking of, tertiary alcohols are observed to be most reactive, and primary alcohols are least reactive in this case. The reason being, in these reactions, that is SN1 reactions, again its mechanism we will be discussing when we discuss the nucleophilic substitution reactions of alkyl halides. In these reactions, carbocations are formed as intermediates, and we know that the order of reactivity parallels stability of carbocations. We also know that tertiary carbocation is most stable, followed by secondary, followed by primary, and methyl carbocation is least stable among the primaries. Primary carbocations, the reason being that these carbocations are stabilized due to plus I effect of the alkyl group as well as due to hyperconjugative effect. So tertiary, that means if the intermediate being formed is a carbocation, so the reactivity of the alcohol will parallel the stability of the carbocation. So now if we carry out the reaction of say a tertiary butyl alcohol, now we've started with discussing how are we going to convert alcohols to alkyl halides. So if we carry out the reaction of a tertiary butyl alcohol to tertiary butyl bromide, this reaction will be carried out easily since we are getting a tertiary carbocation in this. Similarly, if we but the point is, like, if we try to carry out the reaction with HCl or HF, it will not give us very high yields. So while we are saying that we can prepare alkyl halides from alcohols by reaction with hydrogen halides, it has certain drawbacks. What the other drawbacks? We know that the key feature of nucleophilic substitution reaction with hydrogen halides is conversion of OH group into a good leaving group by protonation. That means we are carrying out the reaction in acidic medium. If we are carrying out the reaction with HCl, say, let us say, then in that case, we will have to use additional zinc chloride, because that zinc chloride will make a coordinate bond with lone pair of electrons on oxygen of the hydroxyl group, thereby creating a positive charge on oxygen, which will help in the cleavage of COH bond. So that means the carrying out the reactions is not so feasible. So primary alcohols will not react with HCl or HF, as both chlorides and fluoride ions are poor nucleophiles in comparison to bromides and iodides. So in these cases we have to modify the reactions conditions. And next point that we have to keep in mind, that secondary and tertiary alcohols, similar secondary and tertiary alkyl halides, also tend to undergo nucleophilic rearrangement reactions, that is during SN1 reaction. So what we find, that if we carry out the reaction of this molecule, which is 3-methyl butane 2-ol with HBr, what we find that this molecule will give us will undergo protonation at OH, and this OH will now be eliminated as a water molecule, resulting in the formation of secondary carbocation. So now we know that carbocations have a tendency to rearrange to form more stable carbocations. So this secondary carbocation will undergo a methyl shift, and the methyl shift will take place from the carbon which is adjacent to it to this carbon, resulting in the formation of a tertiary carbocation. And then this tertiary carbocation will react with the bromide anion to give us a product which is different. That is, we will now get here 2-3-dimethylbutane. So this was not the expected product. We were supposing so this is not a very good method, because we will not get the expected product, because the carbocation which is being formed will undergo a rearrangement and give us a different product altogether. So because of such difficulties, now we have several alternative methods for preparation of alkyl halides from alcohols. And as I've said in the beginning of the lecture, that phosphorus and sulfur halides are better halogenating agents, or they to convert OH group into a good leaving group. They provide a better nucleophile, that is a halide ion, to replace the leaving group. In this case, what we find, that the most broadly used, most widely used reagents are for conversion of primary and secondary alcohols to alkyl halides are thionyl chloride and phosphorus halides. So what we conclude from here is that we can use halogen acids to convert tertiary alcohols to halides. But when we have to convert primary and secondary alcohols to alkyl halides, we will prefer using thionyl chloride and phosphorus halides, because the reason being that these reagents undergo reaction under milder condition reactions with alcohols to form intermediate inorganic esters. And because the inorganic esters are formed, the groups, we have good leaving groups that can be displaced by the halide ions. Now we know that the resulting inorganic esters which will be formed, in those cases the leaving group will be better, and that it will be easily replaced by a halide ion. So in this case, what we've done, as you can see on your screens, that alcohol is treated with thionyl chloride when we are getting a alkyl chloride, and similarly when we are treating a alcohol with phosphorus halide, we are getting a halide. So, and the first reaction, that is also known as Darson's reaction, in which we are treating an alcohol with thionyl chloride, is definitely a better method, because in this the HCl and sulfur dioxide, which are formed as side products, are gaseous and they can be easily eliminated from the reaction medium. The second method by which we can prepare alcohols, and it is a very, very important method, is by addition of halogen acids to alkenes. And we know when we carry out these reactions, that is the reaction of halogen acid to an alkene is an example of electrophilic addition reactions, in which we know that where we have a double bond between carbon atoms, that is a region of high electron density. So this will now, the reaction, the HCl will add, or any halogen acid will add across this double bond. So if the alkene is unsymmetrical, like as we've shown, you can see on your screens, then in that case the reaction will take place to, that is, to one of the carbon atoms halogen will be added, and to the other one hydrogen will be added as protons. So the first reaction that you can see is that we are getting propene is being treated with HCl, when you are getting 2-chloropropane. When we treat propene with HBr, you get 2-bromopropane, and when propene is again treated with HBr, but in presence of peroxide, we get 1-bromopropane. So why is it that when we are carrying out the reaction in presence of peroxide, that also of HBr, we are getting a different product as to what we were getting from reaction of an propene with HCl or HBr? So why is this difference in mechanism? So what we know now is that this is a mechanism, the mechanism here will be electrophilic addition reaction. So in this case, the pi electrons of the double bond will act as an electrophile, and an electrophile will be added to one of the carbon atoms, resulting in formation of a carbocation. And in the second case, that means in this, if we are carrying out the reaction with HBr, this pi electrons will make a bond with H plus, and then in the second step they will react with the nucleophile, which may be a bromide anion. Bromide anion will react with the carbocation, resulting in the formation of the product. This is the general mechanism of the reaction. But we know, now let us consider that the alkene was unsymmetrical, and the reagent, as you know, is also unsymmetrical like HX. So alkene, supposing we've taken alkene to be propene. So propene, we say, is unsymmetrical. Why is propene unsymmetrical? Because the C double bond is attached to one of the carbons is attached to 2 hydrogens, and the other carbon is attached to 1 hydrogen and 1 methyl group. So this is a unsymmetrical alkene, that is, the groups on the either side of double bond are different. Whereas when we talk of ethene, then ethene is symmetrical, because we have CH2 double bond CH2. In that case, the substitution on either side of the hydrogens of the carbon atoms is same. So that is a symmetrical alkene. And when we talk of HX, HX is an unsymmetrical reagent because it is made up of 2 different atoms, that is, H is hydrogen and X is an halogen atom. So when we add an unsymmetrical reagent to an unsymmetrical alkene, it follows Markovnikov's rule. So what does Markovnikov rule say? It says that when HX will cross a double bond of an unsymmetrical alkene, it will result in an alkyl halide which is more highly substituted, or in other words, rich will become richer and poor will become poorer. Or the better way of understanding this is, if we go into the mechanism of the reaction, that is, the reaction will take place along that path which will give rise to more stable carbocation. Now, as you can see on your screens here, I have taken an example of 2-methyl-propene. So when we talk of 2-methyl-propene and we are carrying out the reaction with HBr, So what we find that H is going to that carbon which already has 2 hydrogens in it. So the rich becomes richer, right? And that means hydrogen will go to that carbon which is already having 2 more hydrogens, or we can say that the negative part of the reagent will go to that carbon which is attached to less number of hydrogens. So what we find, Br will go to that carbon which is attached to 2 carbons. So this is what the reaction is. Now why does this take place? So when we look into the reaction with HBr, what we find that when we are carrying out the reaction with HBr, we have 2 possibilities. That is, in this case, hydrogen will add to, at the corner, what will we get? We will get a tertiary carbocation. So when we get a tertiary carbocation, to that carbocation, bromide ion will go and make a bond with tertiary carbocation. So that is why we say that the reaction will take place along that path which will give rise to a more stable carbocation. Whereas if hydrogen had added to a carbon which was attached to 2 methyl groups, then in that case we would have got a primary carbocation. So that is not the correct choice. So now here again I have shown you this with another example. That is, in this case we have 2 possibilities. In first possibility, we've added the proton to that carbon which is attached to 1 hydrogen and 1 methyl group. When we do that, we are getting a secondary carbocation. So when the hydrogen is attached to another carbon, in the second case, hydrogen is attached to the carbon which is attached to 2 methyl groups. Then in that case what we are getting is a secondary carbocation. Whereas just we'll concentrate, go back to the first reaction. In the first reaction, hydrogen is adding to a carbon which is attached to 1 hydrogen and 1 methyl group. So when hydrogen attacks to that carbon, what we find that we get a tertiary carbocation. Whereas in the second case, we've taken a hydrogen which is making a bond to that carbon which is attached to 2 methyl groups. So in that case, what happens is we get a secondary carbocation. And we know a tertiary carbocation is more stable than a secondary carbocation. So in this case, the first reaction is possible and the second reaction will not take place. Now in this case, what we've done, we've taken an example of 1-ethyl cyclohexene and carried out the reaction with HCl. Now again the question is, where will HCl go? Whether Cl will go to that carbon in which which is attached to a ethyl group on one side and to another carbon on the other side, or to that carbon which is attached to CH and then to another ring carbon. So what we find that if the carbon which has been numbered as 1, this is a secondary alkyl group, because in this case the carbon is attached to 2 other carbons, that is the carbon containing the double bond, whereas the carbon which is numbered as 2 is a primary carbon because it is just attached to 1 other carbon. So we know that the reaction will take place in such a manner that hydrogen will go to add to that carbon which will give rise to more stable carbocation. That means hydrogen will add to the carbon number 2, resulting in the formation of a tertiary carbocation, which will then react with a chloride anion to give us 1-chloro-1-ethyl cyclopentane. So here again we've done the reactions, and these are the general reactions which I have shown on your screens. And here again what we've shown, the reaction of, let's say, benzyl chloride with chlorine. Now, so this is an example of another reactions. These reactions are, now I would like to go back before we go here. Supposing we were carrying out the reaction of a molecule, say like propene with HBr in presence of as such. So what we'll get is 2-bromopropane will be the main product. But when the reaction of propene is carried out with bromine HBr in presence of peroxide, we get 1-bromopropane. Why is it so? And no other halogen acid gives us this reaction. The reason is that HBr in presence of peroxide undergoes free radical reaction. And in that case, we get H free radical and a Br free radical. And the reaction is initiated by a Br free radical. So when the reaction is initiated by a Br free radical, that means now reaction will take place along that path, which will give rise to more stable free radical. So therefore, the reaction mechanism will be reversed there, and instead of getting a more highly alkylated alkyl halide, we will get a alkyl halide which will be opposite to what we are getting when we are carrying out an ionic mechanism. That is, when we carry out the reaction of propene with HBr, we will get 2-bromopropane, but when we carry out the reaction of propene with HBr in presence of peroxide, we will get 1-bromopropane, because in first reaction the mechanism is ionic, where the reaction is initiated with the attack of the double bond on H plus. And in second case, it is a free radical reaction where the reaction is initiated by a Br free radical. So this is where we will stop today, and in the next session we will continue with the methods of preparation, that is preparation of alkyl halides from alcohols, and then we will take up two important reactions, that is the reaction of from silver salts of acids, which is a Hunziker reaction. Thank you.